Hello everyone, my name is Alex Ferencic. I am a postdoctoral researcher at UC San Diego, and I work with FPGAs. You might be familiar with Corundum, which is the open source NIC project that I've been working on for a couple of years now. So today I've got a couple of big honkin' FPGA boards to take a look at. I think there's a lot of interesting stuff that we can learn from these guys. So let me go ahead and grab one of these things and we'll get into it. All right, so here we go. This is a board made by a company called High-Tech Global. So this is, what was it, the HTG 9200, I think. So these guys have a big Vertex UltraScale Plus FPGA in the middle, and the idea is to provide as much high-speed connectivity as possible to that device. So these guys give you 9 QSFP28 cages on here, and I guess that looks fine. Okay. All right. So the plan that I have for today is to take a look at these boards in detail, because there's a number of things that we can learn about, a little bit about high-speed board design and what some of these FPGAs require in terms of support components. And then what I'm going to do is I'm going to bring up the board. And for these, it's a little bit more complicated because there are some components on the board that need to be configured in order to actually be able to use the FPGA. Primarily, there's a couple of PLL chips that need to be programmed, and these PLL chips provide the FPGA with the required reference clocks for all of the high-speed transceivers. So we're going to take a quick look at the software required for doing that and get everything all set up, and then we'll go from there. And let's see. Once we have that running, then I'm going to run some bit error tests on all of the QSFP channels to make sure everything works. Right, so let's take a look at this board and see what we're working with here. So right in the middle, so actually one thing about these boards, compared to some of the dev boards you might get from Xilinx, this board actually doesn't have a whole lot of stuff on it, right? If you look at some of the Xilinx dev boards, you get all sorts of different I/O interfaces, right? You might have maybe 1 or 2 QSFPs, but then they might give you some SMA connectors, they might give you some HDMI connectors, they might give you a whole bunch of stuff. But this board just gives you a whole bunch of datacom style connections and not really much else. You get that, you get some RAM, you get an FMC, and then the rest of this is all basically just supporting components. Let's see. All right, so first let's take a look at the board itself. So, Houston, my cat wants attention apparently. What are we doing? All right, let's not cause too much trouble, okay? All right, so let's see here. The first thing to look at is the board itself. So all of these transceivers, each one has 4 lanes at 25 gigabits per second. In order to run that over the board, you need some relatively careful board design, and you need good quality traces, differential traces, and you need good isolation between them, because any crosstalk and whatnot is going to completely screw everything up, and you can get a lot of that very easily at 25 gigabits per second. Another problem that you have to worry about is loss and any kind of reflections and whatnot. So this board is going to be, I have no idea how many layers. This board is rather thick. Let's see, do I have a PCI board around here for comparison? Right. Here's something with a PCIe edge connector. So just for reference, that board it's not twice as thick, but it's it's 1.5 times the thickness, something like that. So, all right. So I don't know how many layers are in here, but probably at least 10, and they're all going to be separated by ground planes. So on the top, it's not a ground plane, so you have one signal plane. So we'll have that, and then ground plane, signal, ground, all the way through. I don't know if they have any power planes. From looking at the back, you know, there's a nice big, you know, power polygon fill over here, but they could have some power planes inside the board as well. That's actually one thing you can do at the stack up level. If you put a power plane and a ground plane right next to each other, that'll actually give you a little bit of decoupling, basically, because of the close spacing of those planes. And that can be important when you're using a big chip to get some of that bypassing. Let's see, what else? Another thing that you can look at on some of these boards is just take a look at what the vias look like. Let me zoom in here and we can take a look. So you can see that there are, let's see, where is my field of view here? Okay, so we can see that there are some vias with holes, but then there's also just some vias without holes. And that indicates that this board is using some sort of plugged or capped vias. And the idea behind that is it allows you to put a via inside of a surface mount pad. So usually you can't do that, because if you put a via inside of a pad, when you solder something on top of it, a bunch of the solder is going to go down into the hole, and then you're going to get basically yield issues because the connectors or the components won't be soldered reliably. So instead, in this case, what they do is they actually go in and they plug the via, and then they plate over the top of it after they drill it. And that allows you to put the via directly in the pad. So underneath the FPGA here, that's the idea. Instead of having like a via escape where you have the BGA ball and then you go out, you know, 45 degrees and then you have a via, you can just go straight down underneath the pad. The other thing that you'll notice on this board is that there's a bunch of holes over here. I don't know if any of you have seen holes like that on a board, but you know, right where there should be a via, there's a hole. Well, this is something called back drilling, and this is something that's done when you have high-speed traces that you're trying to run across the board. So we can see back drilling underneath the FPGA here. We can see back drilling over here underneath the FMC. We can see back drilling, let's see, there's more back drilling over here where the SMA connectors are. There's back drilling over here where the QSFPs are. So we can see all those holes that are drilled. And the other thing that's interesting, let me see if I can get this on the camera here. The holes are not drilled the same amount. See, these holes are drilled much deeper than these holes. Quite interesting. All right, so what is the point behind back drilling? Well, the idea is to remove the extra via that's present there. So when you're doing high-speed layouts like this, you need to make sure you don't have any basically stubs. You want to have one continuous trace that doesn't have anything sticking out of it anywhere, because that's liable to create reflections. If you want to learn about why that is, you have to look into, you know, RF signal design or RF circuit design, because at these frequencies, right, at 25 gigabits per second, that's like 12, 13, 14 gigahertz, something like that. The wavelength is very short, and it will bounce around inside of the traces. If there's a stub, it'll bounce off the stub, it'll come back, and it will cause inter-symbol interference and jitter, and that's not good. So there's a couple things you can do to minimize that. One of them is that you can use blind vias, where the via doesn't go all the way through the board. But the problem with that is those are expensive to produce and they can have yield issues. So a cheaper option is to back drill it, right? You just make the via all the way through, and also another thing I should mention with blind and buried vias, the layers that you can go between is restricted by the way the stack up is produced. So it can be tricky to use that correctly. If you need them for other reasons, then you do that. But back drilling is basically free, right? It's just drilling a few more holes. Right. So is there anything else we can learn from the board? I think that's about it. Those are the main high-speed layout techniques that I wanted to look at. All right, so now let's take a look at what kind of supporting components we have on here for the FPGA. So we have the FPGA itself in the middle, and that has a heatsink and fan on top of it. Next to the FPGA, we have basically the only peripheral that's on the board, which is a bunch of DRAM. There's 2 banks of 5 chips of DRAM. Let's see, on the side we have a USB serial port. Over here, we have all the power supplies. So with a big FPGA that has a lot of internal circuitry, it requires actually many different power supply voltages. So let's count it up. These 2 are the core supply, so that's 1. And then here's a 1.2 volt supply, that's 2. And then 3.3 volts, that's 3. 1.8 and 2.5, that's 5. And then we've got 2 little power supplies over here, so that's 7. And then 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. And then there's 2 regulators, 14 and 15, for the termination voltage for the DRAM. So that's what, 15 different power supplies on this thing? That's, yeah, that's a lot. So this one is the core supply. This, well, okay. One thing to keep in mind here, this board is designed for ultra-scale FPGAs, but it has an ultra-scale plus installed that's pin compatible. So you don't need to worry about that. Oops, that screw is loose. Anyway, so there are a couple of silk screens on here that are a little bit different because they are for the ultra-scale that it's originally designed for. Okay, so these 2 supply the core voltage, which for ultra-scale, it's 0.95 volts. This one supplies 1.2 volts, and I believe that is for the DRAM. I think it supplies both the DRAM and the I/O banks on the FPGA that are associated with DRAM. And then there's 3.3 volts for supporting components. I don't think that drives anything on the FPGA. These, the transistors on here are so small, I don't think any of them can handle 3.3 volts. And then 1.8 and 2.5, I think 1.8 is for like all of the I/O on here that's not running 1.2 volts and the config bank. And then 2.5 volts, I believe, is the VCC AUX supply for the FPGA. And then we've got these supplies over here. These are supplying the power supply voltages for the transceivers. Right, so what do we have here? Let's see. This one is marked 1V0H. This one is 1V8H, and this is 1V2H. So on the ultra-scale devices, on this side of the chip, we have 36 GTH transceivers. So this supplies the, what was it, MGTA VCC, which is 1 volt. And then this is 1.2 volt. I think that's the termination voltage. And then 1.8 volt is VCC AUX, or MGTA VCC AUX. I'm not exactly sure what that's used for, but it's required for those to operate correctly. And then on the other side, we've got the 3 for the GTY transceivers. So since this is an ultra-scale plus, all of the transceivers are GTY transceivers. So yeah. Quick side note, actually. High-Tech Global makes these boards, and you would think that if you're paying the, thousands of dollars to get one of these things, they would actually configure the board for the FPGA that's installed on there. But that doesn't appear to be the case, because the ultra-scale plus parts require slightly different voltages than ultra-scale, right? Ultra-scale requires 0.95 volts here on VCC int, and the let's see, the VCC supply for the transceivers, it wants 1 volt. But for ultra-scale plus, it wants 0.85 here and 0.9 volts here. So when I got this board, I pulled out the meter and I checked the core supply and I saw 0.95. So for whatever reason, they left the feedback resistors on here as is for ultra-scale. And for this one, it's running it out of spec, but at least under the absolute max. But for the GTY transceivers, the absolute max is 1 volt. So running it at 1 volt is not so great. So if you know anybody who has one of these things, tell them to check it with a multimeter and make sure they're not running it at the wrong voltage. You got to change 4 resistors to fix that. It's not really that big of a deal, but it's like, come on, you're paying, who knows how much for one of these things. many thousands of dollars, you would think they would put the correct resistors on there. Anyway. Yeah, absolute max is 1 volt, and it was running at 1 volt. That's right. So I swapped the resistors out, and now it's running at 0.9 or so, which is what it's supposed to. So, right. All right. So, is there anything else on here that we can take a look at? I think at this point, well, actually, I guess I can point out some of the clocking components. So, the other thing that you need to run an FPGA, obviously, is clocks. So this thing provides a few different clocks. Over here, we have a 200 megahertz oscillator that's connected directly to the FPGA. On the other side, we've got a 200 megahertz oscillator that goes through a clock buffer. I guess I can probably zoom in a little bit here. Okay, here's the first oscillator, right? This guy. And then on the other side, we've got this oscillator here, which goes through a clock buffer, and that drives two 200 megahertz clocks for the memory. Right above that, we have another oscillator. So this one is set to 156 megahertz, and that one drives this guy right here, which is a PLL chip. So it's got, I think it's got 3 or 4 inputs. It can draw an input from this little oscillator here, or from this guy, and then it has 10 outputs, which are used to drive all of the QSFPs. Well, actually not the QSFPs, it's connected to all of the transceiver sites that drive the QSFPs. On the other side of this, there is another one of these oscillators here, also at 156 megahertz. That one drives another PLL chip, and that drives the GTYs on this side of the FPGA that are connected to this FMC plus connector. Yeah, there's a couple of other high-speed connectors on this side. There's a pair of these Firefly sites. So these accept little optical modules that Samtec produces. I think you can also get electrical cables. Let me see. I have a... I'll just show you what one of those looks like. So this is a little board that you get with the VCU 118. So it's an FMC plus loopback. So we could put that on there and to test those transceivers. But it also has one of their, what do they call this? It's one of their flyover cables. So the idea is that you can mount this QSFP plus, on, at the front panel of your device, and then run these, flyover cables to the FPGA or your ASIC or whatever. But there's actually, so each one of these can take 12 differential pairs, and there's 2 different ways they can be wired. One of them is you have 12 pairs going in one direction. The other way is you have 4 pairs coming and 4 pairs going, basically. So this one is wired with 4 TX and 4 RX, and these are wired, this one has 12 TX and this has 12 RX. So I can't really hook this up here because it won't work. I can't loop it back. All right, let's see, what else do we have on here? Yeah, I think that about rounds it out. So in terms of bringing up the board, the main thing that we need to do is configure this PLL chip, because that's going to allow the use of all of these QSFPs on this side of the board. All right, so I'll go ahead and get all of this set up. Let's see, get some power, JTAG, and, oh, actually, I have the other board with some cables already plugged into it. So let me get rid of this guy. Pulling stuff off my desk. That's not good. All right, here we go. Okay, so this board, I already have some cables hooked up. I've got, let's see here. I've got a loopback. So this is actually, it's a QSFP loopback. And then I've got a pair of, these are CWDM4 optical modules. These are from FiberStore, 100 gig, QSFP28 IR4, 1310 nanometer CWDM4. And then I also have an AOC. This is what a Dell AOC QSFP28 30 meter cable with a gigantic spool of cable under my desk here. And let's see, I also have a pair of DACs that I'll go ahead and plug in as well. All All right, so these are our FiberStore 2-meter DACs, QSFP28. All right, let me get these sorted out here. All right, 1, 2, and the other end here. Okay, 3 and 4. All right, cool. Okay, so let's go ahead and get the rest of this stuff hooked up. First thing, we got the power connection there, and then let's see, we got the serial port there, and then the JTAG here. Okay, nice. Turn this on. Okay, there we go. All right, we got some lights. We got all the power rails turned on. Okay, nice. So next thing I'm going to do is I'm going to take a look and make sure all of those oscillators are running real quick. Let's see here. My scope working? Yes, my scope is working. Excellent. All right, so get rid of that cap. All right, so we can go ahead and test all these guys here. Let's see. So I'll start with this guy. This should be 156 megahertz. Oh, all right. Let me go ahead and change this AC coupling. Okay. Now, what I usually like to do for these guys is actually, do the FFT. There we go. And then I need a cursor. Okay. Nice. What is this? Oh, I'm going the wrong way, aren't I? Oh, I'm on the wrong channel. All right, let me select the FFT. There we go. All right, so that's saying okay. Zoom the other way. Okay, there we go. So this guy right here, that should be about 156. There we go, 156.2. That's exactly right. And then this other guy here, let's see. Oh, you guys can't see that. Okay, there we go. All right. So I was probing this guy over here. That's at 156. And then this guy over here, let's see, probe on the input side of that guy. And that one's a higher frequency. As you can see, that should be 200 megahertz. Yep, okay, 200 megahertz. And the output of that, same thing, 200 megahertz. Okay. So let's see if this PLL chip is outputting anything. Nope. Nope. All right. So by default, when you turn the board on, this PLL is not outputting anything, as I expected. All right. Let's check on the other side. We've got this oscillator here. That's probably also 156. Let's see. Yep, that's 156. And then I've got this oscillator as well. That's a 200. Yep, there we go. That's 200. Okay, and then this PLL is also not running, right? Yep, nothing coming out there. Okay, nice. So the next step is to talk to the board from Python and then to configure the PLLs on this guy. All right, go ahead and switch. Let's see here. Okay. You have to give me a second to get my VM going. Hang on a second. Let me switch back here temporarily. Unfortunately, all of the PLL configuration software is all Windows. All right, let's see here. Houston, what do you want? My. All right, let me switch this back over to that. All right, so let's see, the PLL on this guy. Where is this thing? This is Silicon Laboratories. Ah, okay, there we go. And I want the Clock Builder Pro. Okay. So I'm gonna go ahead and get this thing going. All right, so that's that. I'm gonna let that start up. And while that's happening, I'm gonna go ahead and program the FPGA, right? This is the project that I have already set up. So in advance, I already did the tricky part of putting together the top level Verilog design and whatnot. So we don't need to do that. That took, let's just say, a lot longer than I was originally anticipating. And the resulting XDC file was like 1,000 lines long. So go figure. Okay, there we go. I'll hit program that. Okay, so that's now going to work on that. Okay, so while that's running, let's go ahead and configure the oscillator on here. Okay, so I'm going to create a new project. All right. So this is the SI5341. Okay. SI53, yeah, there we go. SI5341. Okay. So this little tool is what you use to plug in all of the stuff. To plug in all the settings, and then it will compute the register values. So I'm going to call this FPGA, because why not? Let's see. I don't know what device revision is. I think it's a D. Okay, let's see. So IO supply, I think that's correct. I'm going to leave that alone. So the main thing that we need to do is plug in all of the frequencies. All right, so on the board, let's see, according to the schematic, let me double check to make sure I'm doing this right here. Let's see. So the clock generator, that little crystal, or the programmable oscillator, is hooked up to in1. Okay, so in1, I'm going to go ahead and turn that on, enabled at 156.25 megahertz. All right, you're probably wondering, where do these numbers come from exactly? Why is it, 156.25? That's like an oddly specific number, right? Why not like 100 megahertz or 200 megahertz? Well, that's because this is designed for operation with, 10 gigabit and 100 gigabit Ethernet. All right, so let's see if we can get that number out of 10 gigabits per second, okay? Let's see, 10 over 64, well, there you go, right? That's 156.25 is just 10 gigabits per second divided by 64. Another frequency that you'll see a lot is rescaled like that. It's 161.1328125, and sometimes you'll see multiples of these. So you can do that. You can times 2, 312.5. Sometimes you might see 625. Sometimes you might see 322. I know the Xilinx CMAX run at 322. Sometimes you might see 644. I think on Stratix 5, I think you need to supply a ref clock of 644. It depends on what the PLLs, or what the PLLs on the transceivers want. But usually you want to get something that's going to be an integer multiple of the line rate for the best performance. All right, so yeah, so actually what I'm going to do is I'm going to set these things to output. Well, I'll set it for 156 for now, but for the 100 gig stuff, I think it makes more sense to run it at 161. Anyway, all right. So in this case, on this page, we can now plug in all the output frequencies that we want. So let's see. I'm going to go through and okay. So I need to plug all of these into the enabled. That's the downside about these wizards. They don't always make this particularly easy to use. It would be nice if you could plug in one and just say set all to this. Go ahead and get all these things turned on here. Okay. Okay, and these are all going to be LVDS. I'm not sure if it makes much difference LVDS versus LVPECL. Not sure. I'll run that at LVDS for now. I would have to take a look at the datasheet for the for the transceivers on the FPGA. I think it'll accept either. Okay, so what I want to do actually in this case, output 2 drives those Firefly sites, and I want to use those for PCI Express. So I'm going to set that to 100 megahertz. And, oh, what is this complaining about? There might be coupling. I see. So this is kind of the nice thing about this little program, is that it can actually go look for some of these possible problems. So because of this, what I'm going to do is run these at 161. I'm going to go in here, 161, and put the decimal point in here. Okay, there we go. All right. Go ahead and copy that. I'm going to go ahead and replace that. And okay. Now it's happy with that now. So go figure. All right, so I'm going to go ahead and plug all these in. Yada, 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 yada. Okay, there we go. It's all green. That looks good. That's frequency plan valid. All right, great. Let's see if that works. Okay, so I will hit next. And this one is in terms of the, what is this, the DCO. All right, so I think what you can do with these PLL chips is actually kind of step the frequency up and down a little bit. So that's not something that I need to do right now, but it's a capability of these chips. They got a lot of features. All right, maximize number of low jitter outputs. That's a good idea. That's fine. That's fine. Okay, so now what we can do is save the design to a file. All right. So I'll do that. And then what we can do is export the register settings. Okay. What was it that I wanted? I think it's a register file. So a CSV file. Okay, that looks good. So if we do preview export, this is what it generates, right? So this has all of the addresses that you need to write to and all the values that you need to write there. So the idea is when you run this, or when you send these values to the chip, then it will start up with the configuration that you need. Okay, so I'm going to go ahead and save that. Sure, that looks good. Okay, and now let me get this out of the VM so we can actually try it out on the device. Okay, go ahead and get rid of that. Okay, and put that away. All right. So this here is the Python script that I've been putting together to talk to this thing. I just remember that the non-volatile flash can only be written once, or only written twice. I'm not going to write it to non-volatile. I am just going to load it into volatile flash. Yeah, I think once you've loaded it, then you can write to some registers which will kind of commit that value to the non-volatile side of things. So I might do that. Actually, there's one other interesting feature about this board. Let me switch scenes again here. Okay. Where was this guy? Oh yeah, over here. I haven't seen this on a board before, but they give you a PIC microcontroller right here. U49 is a PIC microcontroller, and then there's a programming header here. And that only sits on the I2C bus. So what you can do is, after you've generated this configuration, instead of burning it into the PLL, you can write a little program that sits on the PIC chip, and then when you turn the board on, it'll configure whatever you want in terms of I2C. So you don't have to do that from the FPGA or whatever. So there's also this aardvark connector. So there's a little box you can get that's USB to I2C, USB to SPI. So you can plug that in here and configure the I2C bus that way. Yeah, a couple of different options. But I'm just going to configure it through the USB port for now, using the design that I've loaded on here. Okay. Let me switch back. Let's see here. Okay, there we go. Let's see. So this particular piece of code is set up to talk to the design that's running on the FPGA. And let's see. So I guess one thing I should do before I start playing around with this too much is just give you a little bit of background on what this XFCP thing is, because this is something that I've been kind of piecing together over the last few years that kind of came out of, it's kind of come out of a series of different research projects that have, you know, kind of slowly become more and more complex. So a bunch of years ago, I had to put together kind of a bit error test design on a big honk on Vertex 6 FPGA, and we needed some way to control it. So I made a very simple kind of serial port to wishbone interface, which worked fine for that particular experiment. But when I went to IBM to work on some of the switch testing stuff that we were doing there, we had to build a much more complicated design on the FPGA in order to make everything work. And I needed something a little bit more flexible than simply a wishbone, you know, the serial port to wishbone connection. So my initial idea was to do that, but I quickly realized that it would end up being a gigantic pain to basically keep all of the configuration synchronized between the FPGA design and, you know, the Python. So actually, let me show. This is what the setup looked like that we were trying to put together. So on the FPGA, we had, you know, a bunch of different modules, right? We had you know, a pattern generator, which was going to be generating the test data. We had a switch control module that was controlling the silicon photonic switch. We had a trigger generator that was generating timing signals for all these other components. And then we had an error detector and pattern checker that was looking at the data coming off of the receiver chip that we were testing. So this is a lot of components, and some of these things are actually replicated multiple times. So it's like we had 2 FMC connectors on the board, so we actually had 2 of the error detectors. For the pattern generators, we had 1 of those per transceiver. We had a bunch of other stuff on here. So what I wanted to be able to do is have a framework where I can just throw some stuff on the FPGA, connect it together, and then just connect to it from Python, and it'll figure everything out, right? I didn't want to say, okay, I'm going to take this module, I'm going to assign these addresses, I'm going to take this module, I'm going to assign those addresses, and then I'm going to go over to Python, I'm going to plug in those addresses. That's just a pain. And every time you change something in Python or change something in the FPGA, you got to keep everything, you know, synchronized. It was just a nightmare. So what I ended up doing is I sat down, I'm like, all right, I need a better solution for this. And I came up with the idea for XFCP. And the idea is to use, instead of something like a memory mapped interface, to use basically a packet switched interface and to use source routing, right? So the addressing scheme is based on which switch port stuff is connected to. So you can set up a hierarchy of switches, and then based on the destination port, it'll get routed out that port. The other thing I realized is that with the LUTs on the FPGA, one LUT is a 32 by 2 RAM, right? So with 4 LUTs, you can store 32 bytes. So all I need is a packet type that says, give me your ID information, and then you can just play out the contents of this little 32 byte RAM, which takes 4 LUTs. So it ends up being a super efficient implementation on the FPGA, but also super flexible, because I can just take this thing and enumerate everything on the board directly from Python. All right, so let's see. So we're going to see this in action here. I'll go into Python. Okay, so I have my test script and then also this XFCP control thing. So here is, well, that's the configuration I pulled out of the VM. But let me go ahead and run XFCP control real quick here. Yep, okay, there we go. So this shows all of the stuff in the design, just like that. I didn't need to configure this. This XFCP control thing is exactly the same that I use for, this will talk to any design that uses XFCP. It doesn't need to be aware of exactly what's on the FPGA. So this goes in and it detects, well, here's your I2C node that's used for talking to all the components in the design. And then it's got switches, this one for all the GTYs, and then I have 1 switch for each quad. And then inside of that, I have 4 DRP interfaces for the individual channels. And then I have a DRP interface for the PLL. right? So using this, you can go through and, well, so this one just says everything's a memory node because this is not aware of what a GTY transceiver is. So instead, what I'm going to do is I'm going to run my test program. Let me show you what that looks like. So this is going to go through and it's going to enumerate what's on the I2C bus. Actually, I guess I can uncomment this so it'll enumerate everything. Then it'll configure the PLL chip using, let's see, yeah, using the configuration file here, right? It'll actually print out some information about the design, wait for the PLL to lock, and then this will also print out information about the installed QSFP modules. And there's some interesting information in there. And then it will place the transceivers in PRBS 7 mode, reset the transceivers, and then eventually it will run a bit error rate test, right? It'll place the transceivers in, let's see, where does it do that? Oh, I guess that's what we're doing up here. Yeah, so this places them in PRBS test mode, and then we clear the error counters, and then we wait a short time, force some errors, read it again, and we should see all channels locked and one error on each channel. That's the idea. Okay, so I'm gonna go ahead and run that. Okay, so that went ahead and dumped all the QSFP module information. So let's see what it did. Okay, so now you can see that these are showing up as the GTY channel nodes and common node. So you can poke at these from Python. This is what that, whoops. Oh, I pulled that into a window. Okay, there we go. So this has all of the registers defined in here. So you can go through and you can, set reset done or change the polarity or whatever. Actually, some of these are going through the DRP interface and some of them are not. Actually, I guess for the channel nodes, I don't have any registers defined over DRP except for, I think, the error counts. Everything else are basically stuff in my wrapper code that's driving ports on the module. Okay, so this enumerates all of that, and you can see it's got all the channel nodes and the common nodes, and then it goes ahead and configures the PLL chip, right? So originally it read some design ID. I guess this is the default design ID that it starts out with, but after running it, it now has the design ID set to FPGA. Waits for the PLL to lock, and then this is all of the information from the QSFP modules that are plugged in. So the QSFP modules will give you information about, it not only has the vendor name and part number and serial number, it also has status information about the connection. So it says LOS, indicating whether it's getting a signal or not. It tells you whether there's a TX fault. It tells you whether the CDRs are locked. It also shows you the temperature. So some of these are running actually rather warm. Yep, those are pretty warm. It shows you the supply voltage. It shows you the RX and TX power levels. And it also shows you whether the CDRs are enabled. So I got that for each module that's plugged in. So these first two are the Dell direct attached copper cables. And the thing that's cool about these guys is that you can actually look at the serial numbers and you can see what cable is attached to what. So that's not something you can do with regular Ethernet cables. When you're using direct attached copper cables or active optical cables, you can trace them just by looking at the at the serial numbers at both ends of the cable, which can be a useful capability. And then I got the DACs. So these just show up as all zeros here because, well, it's a DAC. It doesn't have a laser in it. Let's see. So those are the DACs, and then I've got, right, here's the fiber store CFP, or not CFP, the CWDM module. These things are drawing quite a bit of power in terms of the laser bias. That's running pretty hot. But interestingly enough, they're running cooler than the Dell modules. I'm not sure why that is. I don't think they're getting much more airflow. But as you can see, they're not very efficient because we're putting in, 50 milliamps of power on each of the lasers, but they're only giving you about, between 1 and 2 milliwatts of power. So, yeah. Anyway, Once all that's done, and it's printed all that out, then we can look at the error counts, right? So this is basically immediately after reset, it dumps all the counters, and well, as we can see, some of these are not working very well, right? So these are not locked. These are not locked. This one is locked, but it's got a lot of errors. These are not locked. Here's a couple more that are locked, but have a bunch of errors. So that's interesting. And then what the code does is it forces an error on all of the transmitter channels. And in this case, we can see a lot of the channels that were locked and didn't have any errors now show one error. So that's expected, but some of these are showing a lot of errors. So we're gonna have to do something about that. All right, let's see. So one thing to keep in mind with this high-speed digital communication, the signal quality is extremely important, and it's actually quite hard to make this thing work right out of the box. So there's a lot of features inside of the transceivers that are used to try and improve the signal quality to actually be able to bring up a link. So there's two components to that. I'll pull up the, let's see, the manual here. Let's see, can I zoom into this a little bit? Yeah, okay. And we can take a look at a couple of these features. So in the receive direction, now these components are, well, actually, before I do that, let me go show you what the overall transceiver looks like. Let's see. I think there's a general block diagram of these guys. Yeah, here we go. All right, so this is what the transceivers look like. In the transmit direction, this is everything. Then you have the transmit driver that goes out onto the wire or the fiber. Well, in this case, it goes out under the wire, and then you'd have a QSFP if you want a fiber. In the receive direction, you come in and you go through all this stuff and back to the fabric. So the stuff in here is mixed signal logic, right? This is going to be analog and mixed signal. This is the black magic part of the transceiver, basically. All of this is just digital logic, nothing particularly special. So let's see. For the BER test that is running right now, we use the pattern generator here to generate test data, which gets sent through the transmit side. In the receive direction, let's see, there's a PRBS checker right here. So the data comes in and you can run the PRBS checker. So the interesting thing is you can actually run the PRBS checker without affecting anything else, although that's of somewhat limited use because if you're not sending PRBS over the link, then the PRBS checker doesn't help you at all. Anyway, let's see. So in the receive direction, there's equalization that's used to try to improve the quality of the link. So let's just take a very brief look at that. Let's see, so RX equalizer, there's two types. There's a DFE and there's LPM. So what the equalizer is trying to do is compensate for high frequency loss. These signals, they basically consume bandwidth essentially from DC up to maybe 0.7 times the data rate or something like that. So at 25 gigahertz per second, I mean, we're talking like 18 gigahertz or something like that. It's pretty crazy. And actually moving this across the circuit board is not an easy thing to do, or moving it through cables or just sending it around is a problem. And what ends up happening is that you get high frequency loss. That's kind of the most important problem that you run into with these connections. So let's just think about it for a second. What happens? What effect does that have on the signal if you're going to remove some of the high frequency components? Well, where are all the high frequency components in the signal? They're not in the high level or the low level. They're all in the edges, right? Whenever you have a very sharp edge, that's where all your high frequency components are. Okay, so if you attenuate the high frequency components, you're taking those components out of the edges, and that means you're going to slow down the edges. You're going to round out the edges. And what this does is it creates intersymbol interference, right? Because it means that if you send, say, a bunch of zeros, then the next bit that you send is not going to come up as high as if you sent a bunch of ones, right? Yeah, so what equalization tries to do is to restore some of that high frequency information. So LPM is a linear equalization, and the idea is, okay, let's just build a filter that can provide some gain at those higher frequencies, and hopefully that'll be able to restore some of that and sharpen the edges up such that you can actually, receive the data reliably. So that's one option, and I think this is used by the transceivers when they're running at lower line rates. At higher line rates, they use something called decision feedback equalization, or DFE, and this is a block diagram of what that looks like. Now, it looks really complicated, but all of this is just duplicated. Okay, so here's how it works. The signal comes in here, it goes through linear equalization to kind of bump up the high frequency components a little bit, and then there's an adjustable amplifier, and then the output of that goes through this is going to be an analog adder. I will say it's not necessarily built exactly like it's drawn here on the FPGA, but it has the same effect. Right, so you can think of it as performing an analog addition here. The output of that goes through a threshold comparison. So at this point it's analog, at this point it's digital, right? Zeros and ones. So this then goes through the deserializer and to the FPGA. But this is also sent down an array of, a string of flip-flops basically, and these bits get delayed. At each point, that bit is then fed through kind of a controllable weight. The outputs of these are then added together and looped back in here. And the idea is relatively simple, right? If you have a big long run of zeros, well, you probably want to look a little bit more negative for the edge when you get a 1 because of that high frequency loss rounding off the edges. Or if you get a bunch of 1s, you might want to look a little bit higher. So that's the idea. And then there is an adaptation controller, which can look at the bit rate, or not the bit rate, the error rate, and adjust all of these coefficients to try to minimize the error rate. That's the idea. So this can do a lot, but unfortunately, it's not perfect. It's not going to make a particularly bad link work. So what we need to do in that case is we actually need to go to the transmit end and do something called preemphasis. So this is where the transmit driver comes into play. So in this case, there's actually 3 drivers that are connected to the output pin, right? So this one is called the main cursor, or the main driver. So this one is actually going to be sending the data. And then we have 2 other drivers. This one is called the preemphasis driver, or the precursor driver, and then this one is the post-emphasis driver, or the post-cursor driver. And these are driven with basically delayed copies of the data that you're sending. So this one gets so we're going to call this one at time equals 0. It's delayed by 1. This one is delayed by 1 less, so this one will get the data bit before you're actually sending the bit, and then this one will get it after because it's delayed by 2 cycles. And what we can do is we can adjust basically the drive strength of each of these guys to change the shape of the output waveform. Okay, so let's see what that does. Let me go back to this guy. Okay, let's see here. Okay, so the first thing I'm going to do is I'm going to check to see if maybe we are seeing just overall loss, right? Not frequency dependent loss, but just loss. So if we crank up the output swing, right, we're going to hit this harder, we're going to give it a bigger swing, we're going to see what happens. So let's see, we've got 3 channels that didn't lock here, and we've got 3 channels over here that have a pretty high error rate. Okay, let's try that. Let's see what this looks like here. Oh, okay, so those locked, but these are actually doing even worse. Interesting. So we've got, well, actually, maybe not. I think they're doing a little bit better. So previously, looks like we had about 6 channels. Let's see. Now we had 3 here and we had 2 here. Okay, so 5 channels that were not doing so well. And all right, so it got a little bit better. Okay, but not a huge change. Okay, so I'm going to set that back to what it was at before. And let's go ahead and add a little bit of, let's see, I'm going to try, I'll try like 3 for now. We'll give it a little bit of both the precursor and the post-cursor equalization, and we'll see what that looks like. Okay, that's a little bit better. We still have one here that didn't lock, and one here that didn't lock. But all the other ones that did lock, no errors. Okay, let's turn that up a little bit more, and we'll see what that looks like. Still have one that didn't lock, but that's getting better. All right, let me turn this up a little bit more. How about instead of 7, I'll put 10 in there. We'll see what that looks like. Let that run again. Okay, and we have a different one didn't work. Okay. All right, let me turn this one up all the way, and we'll see if that makes much difference. All right, so now a few of these didn't lock, so we're hitting it maybe a little bit too hard. Actually, which one didn't lock before? Oh, I think that was one of the DACs, wasn't it? Okay, let me try turning this down a little bit. What can happen if you hit it too hard is you can get distortion, right? The pre-emphasis, it only has so much headroom to work with, and eventually you need to start decreasing the actual signal level in order for that to work. Interesting. So this one is still on USFP3. So what I'm doing here is I'm setting these channels on, or setting these settings on all the channels, but what we might need to do actually is set different settings on different channels for this to work. So this is this can be a somewhat tricky process to figure out. And so on the receive side only, it's called adaptation when you're adjusting the the DFE parameters. But if you want to adjust the transmit side, that's usually called link training. And that's done in some protocols. So I know PCI Express does link training. Ethernet, I think, can, if you have the right settings turned on. I think you can do auto negotiation and link training. Oh, okay, there we go. Hey, we have all the channels locked, and they all are reporting, one error. So there we go. We got that tuned up. All right. So that looks pretty good at this point. So unfortunately, I don't have any of the other connections on the board set up to use with this framework. Only the QSFPs, but those seem to be working at the moment. The other thing is that for 100G Ethernet, generally what you can do is use something called forward error correction. I think that's actually a requirement for the 100 gig Ethernet standard, is to support what's called a Reed-Solomon FEC. And the idea behind that is you can actually tolerate a low level of errors because the FEC will be able to correct for them. So even if the link quality is not 100% perfect in terms of, the receiver is actually picking out every single bit absolutely correctly, once you add the FEC on top of that, it can correct quite a few errors. And this actually becomes a much bigger deal when you're using, let's see, coherent optical connections. And in that case, they actually need to use a pretty serious amount of FEC, because they're talking about error rates of like 10 to the minus 3, where 1 in 1,000 bits or something is flipped. Yeah. Anyway, I had a question. What line rate? Let's see. These should be set to just a standard 25G line rate. So there we go. This is set to 161 megahertz ref clock and 25.78125. So why such a weird number? Well, it's 10G times 2.5. All right, let's see. I think that's about all that I had planned for today. It would be fun if we could look at this on a scope. Unfortunately, I don't think my scope is fast enough for 25 gig. We can try it though. If you guys want to see this on a scope, I could set that up. What do you think? Should we set up the scope? Talking about FEC on that side. Yeah, so the FEC for 100 gig Ethernet is, where is that implemented? Yeah, it's implemented inside the PCS PMA. Yeah, that's right. So for 100 gig Ethernet, it actually takes the 66-bit blocks and repacks those into much larger blocks. Yeah, let's do it. All right. Let's see. I am going to need to get a couple of things dug out to hook this up. And let's see here. Okay, so unfortunately, I don't have the SMAs on this board operational, so I'm going to have to switch to a different board. Let's see. I'll get all this stuff unplugged here. Carefully. Okay, get these guys out of the way. All right, so the board I'm going to use for this, because I actually have a design ready to go, and I actually have RF connectors on it, is my VCU108. All right, there we go. So the VCU108, it has this crazy bullseye connector on it. These are actually kind of cool devices. And you can see where all of the capped vias are in this case. Let's see if I get that any closer to the camera. Can I get it at the right angle where you can see that? Yeah, there we go. Yeah, now there you go. You can see where all of those capped vias are around all of those pads. But the great thing about these is the cost of the connector on the board is basically zero, and you don't need to solder on some super crazy expensive RF connector. You can basically just whack down the footprint and you're good to go. Okay, so I got that. Let's see, I need some cables. All right, let's see here. So I need two cables here. I need this JTAG and the UART. All right. Now, fortunately, I happen to have a breakout somewhere. Where did I put it? Here it is. For the bullseye. So this guy, whoops, I need that. Okay, okay. So this guy breaks out that bullseye connector to a bunch of SMAs. So that's what the business end of the connector looks like, right? And I need this little elastomer thing for the ground. All right, let's see here. Okay, we'll get that on there. All right. Let's see. So that's going to go on. Gotta get the keying right. Ah, there we go. Okay, cool. Okay. The other question is, how am I going to trigger this? Oh, I can put one of the transceivers in a square wave mode. That's right. Okay, I will do that. That sounds perfect. Okay, so there is that. Now let me get my scope probes. Let's see here. All right, I need to get these things configured. So I'm going to use one of these for the data and one of them for the trigger. And then I'm going to have to pull up the schematic as well, so I actually get these on the correct pairs. Let's see here. Oh, I should also turn on my scope. Where's the button? All right, there we go. Okay. All right, so there's one, and then I need the other one. let's see, so that one's, so the 12 gigahertz one I will use for the data, and then the 10 gigahertz one I will use for timing. And I guess if the bandwidth is too much for my scope, I mean 12 gigahertz, while a lot, is probably not enough for 25 gigabits per second, but we'll see. I think we're going to have a very crappy looking eye. Not because the eye is that crappy, but because the scope is not fast enough. Okay, let's see here. So this is the 10 gigahertz, and this one is the 12 gigahertz. All right, so I'll put this guy on channel 1, and I'll put the other one on channel 3, and let's see here. Gonna move that, okay. Okay, there we go. There's one. And let's see. There is 3. All right, cool. All right. Let's see. Let me double check what the pairs are here. Let's see. Okay, so I'm also going to go ahead and get this board programmed. Let's see. Okay, that's running. Let me pull up the VNC viewer so we can actually see what that's doing. Let's see. That one. What was I doing before? Yeah, there we go. Okay, cool. Connect. Okay, let's see here. All right, let's see. I'm going to put this, I don't want full screen. Yeah, I want to do that. Okay, and then I'm also going to turn off color grading. That's better. Okay. All right, let's see here. So I need channel 1 and channel 3. And let me get my schematic. Not that one. Is it this one? Yes. Okay. Let's see. So I'm going to take EX0, which is on 15 and 16. All right, so 15 and 16, and I'm going to put that on this probe. Oh boy. Downside about these things is you got to go hunting to find the cable you want. Let's see, 15, and okay, there's 16, and I think 15 is going to be, I think it's going to be right next door. This one? I think that's right. That's 17, okay. This one? Yeah, there we go. All right, 15 and 16. All right, okay. So 15, I'll put that on the positive side. And 16, I'll put that on the negative side. Okay, there's that, and then I need this guy. I'm going to put that on, get these caps out of the way. All right, that one is going to be on the other side. I'll put that on TX3, which is 5 and 6, it looks like. Okay, 5 and 6. All right, 5 and 6. Where are we? Here's, I guess that's 6. They didn't underline this, so I think it's 6. I don't think it's 9. Okay. 6, and then 5 is going to be one of the ones right next to this here. This one, maybe? That's 7. Okay, maybe this one. Okay, that's 5. Okay, cool. So we'll put 5 and 6 on here. Okay, 5, and then 6, and then I'll get all this out of the way and turn the board on and program it. Okay, there we go. 5 and 6. Now I'll turn this guy on. All right. Woof, what a setup. Okay. Let me go back to here. And okay. Did I hook one of those up backwards? That's 15 and 16. I think that's right. Let me make sure I got that right. Okay. All right. Let's go ahead and program that, and then we'll take a look. Was it that one? No, it wasn't. It was okay. This one is what I want here. Here we go. VCU 108. I will program that. Excellent. I got to program it, and then I need to connect to it from Python. Oh, something is not happy. All right. Let's see. Vivado didn't want to talk to that. All right. Maybe I need to close Vivado here before that'll work. All right. Let me try that one more time. It should be pretty quick once Vivado decides to cooperate. Get that one put away. Okay, there we go. It detected it. So this board has an ultra-scale device on it, XCView 095. So this one actually has both GTH and GTY transceivers. And they have the GTY transceivers hooked up to the bullseye sites. So, okay, there we go. Let's see. Okay, there we go. So we have the QSFP, CFP2, and bullseye. All right, very nice. So that went ahead and ran across all of those. And let me see what the scope is showing. Wait, why is this 3.32 volts? That would explain a few things. Okay. Still seeing a pretty significant difference between these two. Interesting. Don't zoom. All right, so now what I need to do is I'm going to use this second channel here as a trigger. So let's see. What I need to do is go into, oh, where was that file? Get this over here. Oh, I think I have it up. Okay, there we go. Yes. All right, so what I need to do now is I need to change the pattern generator mode on that fourth channel. Oops. Okay, so I'm going to put this, let's see, which channel was that? This is 343. And I'm going to put this in, what mode do I want? Thought I had this up. Here we go. All right, so I want the square mode. Okay, SQ. Okay, so I'll run that. That puts this now. Okay, that's better. All right, so what this does is I'm generating basically a divided output on channel 3 here. So what I'm going to do is, well, I'll just go ahead and put this at 0, right? And then I'm going to trigger on channel 3. 0, okay. There we go. All right, so I'm now triggered. All right. Now I can turn off that channel and we can take a closer look just at channel 1. And this is not looking all that great. Why is this at a negative offset? That does not seem right here. Did I not get this thing plugged in all the way? Is that what happened? Nope, okay, that seems fine. And it says 15 and 16. That's odd. That should be centered around 0. So TX0, okay, 15 and 16. All right, well, why don't I try a different channel then? How about I do channel 1, 13 and 14? Not sure what's going on with that. All right, 13 and 14. It was right there. Perfect. I will try that instead. Guy off. Problem is when you have a lot of different moving pieces, getting everything cooperating can be tricky. Possible I didn't screw that bullseye on all the way or something. Okay, there we go. That looks closer to what I would expect. Okay. All right, let's see here. Okay, saying the ILA is amazing. Yeah, the ILA is extremely useful, but you have to know kind of what you're looking for, unfortunately, because the sample depth is so small. All right, let's zoom in on this guy. Go ahead and put this, what does it, 0? Yeah, okay. 0, cool. All right, so, yeah, that looks really bad. And I think the problem is entirely the scope not having enough bandwidth. A heck of a lot of bandwidth, but it's not enough for 25G. Let me see if I put this in color grade. Okay, so I'm going to do a couple of things here. Yeah, that is not a very good looking eye diagram. But I guess the idea is you can see what the high frequency loss does to the signal, right? Because we have, you know, your little 1010 transition over here that's just going right down the middle, and then you've got you know, a longer period transition here. The idea behind this type of diagram is just to stack up all of the possible transitions at the same time. So from this, you can kind of look at the overall signal quality. And what you're looking for in this kind of a diagram is to look at how open these central eyes are. All right, so I'm going to actually change the PRBS mode here. I'm going to make it PRBS 31, and we'll see if that does anything. Okay, where is the right one? Yes, I'll run that, and we'll see if that changes anything. Okay. So one issue with something like PRBS 7 is that it's such a short sequence. You can get basically some intersymbol interference, and it hits you a lot harder than for something like PRBS 31 because it's much less regular, right? PRBS 7, it's 127 bits and then it repeats. PRBS 31, you're sending billions of bits before it repeats again. Okay, so let's see. So with this setup, I don't have any, I haven't changed any of the transmit parameters off of their defaults. So what I'm going to do is basically the same thing that I did before. Go here, and I'm going to go ahead and grab these values here. And I'm going to go ahead and set, well, I'll set both of these to 0, right? And I'll set that to 10. So we're at a known baseline. Come on, there we go. All right. All right, let's see here. Okay. So that's basically what we were looking at before. All right, so let's see what happens if I start giving this some equalization here. What if I set this to 7? Okay, let's see what happens. What we're hoping to do is open up these eyes in the middle, make them, you know, shrink this big band at the top. That's kind of the idea. So let's see if that did much of anything. It looks similar, but I think it's a little bit better. All right, let me go ahead and crank this up a little bit more. Let me put F in here. These are all 32-bit, or sorry, 5-bit numbers, so they range from 0 to 32, or 0 to 31. Right, let's see here. All right, so that's starting to look a little bit better. We can actually see through the eye now. This is getting a lot smaller up here. So one thing you might notice is that I think the overall amplitude has dropped a little bit. And that's fine, because what we're trying to do is just push a higher fraction of the power up into the higher frequency range. And when you do that, you sometimes have to sacrifice by moving some of the power from the lower frequencies. And that results to just an overall lower amplitude. But after you get all the loss of going through the cables and then having the front end of the amplifier and the probe and whatnot, or the front end amplifier and the scope and the probe and whatnot, that you lose all that, all the high frequency stuff. So you end up with, well, in this case, something that's still not flat. But the idea with equalization is you want to end up with something flat. All right, so let me try like 1.7, go up a little bit higher. Let's see, if we hit it all the way, what are we going to get? Okay, so that's, I suppose, looking a little bit better. In fact, I could probably zoom in a little bit on that guy. Yeah, okay. Actually surprised. This is actually a halfway decent looking eye. I'm not going to say it's perfect, but considering that this is only 13 gigahertz bandwidth scope, this is actually somewhat reasonable. So yeah. So you can now you can see kind of what the impact of the preemphasis parameters have on the quality of the signal. So yeah, in this case, this is not looking too bad. Now, one thing that you can actually do on the Xilinx transceivers that I haven't played around with yet is something called iScan. They actually have the capability to measure this kind of information by offsetting the sampling point. So as far as I'm aware how it works, what they do is they have a second sampler that you can offset in time and in voltage from the main sampling point. So if you sample the main point here and you sample another sampling point up here, you can then count how many times you get a different measurement between those 2 points. And using that, you can determine basically the shape of this eye. And you're measuring basically this opening here. So using that, you can determine if you have, some horrible jitter problem or something else. And, you can get an idea of what this looks like. So I think like the iBert tools probably have that all set up to do it. I think I need to add a few more ports in my Python code, but I should be able to do that using Python. Unfortunately, it doesn't work right now, but at some point I'll probably get around to setting that up because I think that would be a pretty useful tool. Yeah, because you don't necessarily need a scope like this to look at this. So the scope that I have is actually, it's a real-time scope. Usually people use sampling oscilloscopes to look at eye diagrams like this because they tend to be, well, a little bit more economical than a real-time scope of the same bandwidth. The flip side is they can only be used to look at repetitive signals, and in this case we're just setting up a PRBS, which is good enough. Yeah. Okay. The other thing I can do actually is let's take a look at what happens if I drop the data rate down. So what I can do here is actually change a setting in the PLL, which will cut the line rate in half, and we can see what a really nice eye diagram looks like. Because if it looks this good at 25G, well, let's see what happens if it looks at I guess 12.5, whatever half of that is. Let's see. So I'm going to go ahead and clear all these guys out. I'll set that to 0, and then I need to go look up what the parameter is. One moment. I need this guy, and this is going to be, this is using QPLL1. I want to change, what was the parameter? It's not ref clock div. It is clock out rate. Yes. I think that's right. That should be 1 bit. Okay, so I want to set this. I set that to false. Okay, cool. Let's see what that looks like. Oops, there we go. All right. So I will go ahead and I will clear that out. And I need to zoom out a little bit here. And also there. There we go. So now we're running at half of the line rate. So this is what you might see if you had a scope that was, you know, double the bandwidth at 25G. So in this case, we're running at 12.5G, and this is what you see basically with a lot less, you know, high frequency loss. You can actually get a reasonable picture of what these eyes look like, and you can see the various transitions here all stacking up, and you can see also here there's kind of a little hump. I'm not sure what's going on with that. Anyway, so let's take this and let's add a little bit of pre-emphasis, and we'll see what happens, right? I'll set this to maybe 7. Okay. All right, and now I will clear this. And there you go. You can see how it cleans up the top and the bottom of these eyes here. So that looks pretty good, actually. Yeah. Oh, so you're asking about the scope probe. Yeah. So in this case, I'm not really probing it per se, right? It's possible to do that, but in this setup, I'm literally just connecting the transmitter directly to the scope. So the scope is loading it at 50 ohms as if it was the receiver. If you wanted to probe it, there are methods for doing that. I have not done much of that myself. Yes, it absolutely can screw up the signal. Let me change to the desktop view here. Okay, let me see if I can hunt down one of those probes real quick. Let's see here. Okay, does this one have any of this stuff in it? Yeah, okay. So if you want to probe a board with some of these high-speed probes, then you can use these solder-in probe heads. Now this one is not solder-in, but this one you solder in a couple of resistors, and then you connect the probe to that. So yeah, obviously when you're doing something in circuit, this is going to affect the performance. Oh, actually I have a solder-in one. Here we go. Here's what a solder-in probe looks like. So this is what you can put, if you want to connect to a signal in circuit. You literally solder this in, and then this plugs into the probe, which then goes to the scope. So let's see, and the probe, if you're not familiar with this kind of probe, it looks like this. So this is the probe amplifier. It's an active probe. So then these guys will plug in like that. So you end up taking that, and this gets connected to the circuit. Yeah, so I've not done too much probing of this type. Usually, when I'm hooking something up, I'm going to just be hooking it up directly to the receiver, like I did with this setup here. All right, let me get this packed up. Yeah, okay. Yeah, so I mean, if you're going at maybe a couple of gigahertz, these aren't too bad, but if you're going at, these scope probes are, 12 gigahertz, yeah, I don't think the signal would look particularly good. The other thing is that you actually need somewhere to probe, and on this board, where are you going to probe it, right? Most of the connections on here are going directly from the FPGA to, these various optical modules or whatever, and nothing is really visible anywhere to even get one of these resistors on there. So you would have to, I don't know, maybe take apart one of these module cages or something to get at the pins. So just getting in to probe stuff can be a huge problem. So this is where, if you can use the iBird, if you can use the iScan features, then you can get a sense of what's going on in the circuit, which can be way more useful than trying to figure out how in the heck to hook up a scope. I mean, the same thing with the ILA, right? I mean, if you wanted to hook up a big external logic analyzer, you could, but where, right? You don't really have, you could maybe come in through FMC or something, but you have, how many pairs are going through there? Like 64 pairs, something like that? Yeah, it's, it's not that many. So, and then you have to worry about signal integrity and skew and whatnot. But if you're running that on the FPGA, in system is the way to go. It would not surprise me if, basically any modern series even something for an ASIC would have this type of capability built in, even if it's not for an FPGA, because you can talk to it from some, internal configuration interface or over JTAG or something to, debug kind of the analog side of it to make sure things are working at the board level. I mean, even things like Ethernet PHYs, like this has a Marvell PHY, and this is hooked up to the FPGA using SGMII. I'm pretty sure you can actually go in over the MDIO interface and flip this into like a PRBS mode. I know you can do that with things like with analog to digital converters, right? Let's see, what is it called? There's a protocol, JES something or other, where it's like a multiple serial links that are used to hook up a high-speed ADC or DAC. Those have all sorts of debugging features where you can flip the ADC to generate specific bit patterns that you can use to test all the links to make sure it works. Otherwise, I mean, you have to feed in some test signal to flip the bits that you want. That it's, it's a pain. It doesn't take up that much extra silicon area to add some of these debugging technique, or some of these, debug components that make this stuff a heck of a lot easier to use. All right. Let's see. I think that about, yeah, there we go. JES 204B. Yeah, I've not done anything with that personally, but yeah, there's that's another tricky protocol to work with, I think, or so I have heard. If the ADC supports it. Wait, yeah, that's true. Definitely not ADCs are going to be JES. There's a lot of parallel ones, but yeah, and the parallel ones are not JESed. I guess this is where like the Xilinx RF sock comes in, right? Because that guy has all that stuff integrated. So, if you want to go that route, obviously you pay for it, but it can make the board design much simpler. And you get all of that capability in a much smaller package. Anyway, that's about all I had planned for today, including firing up the high-speed scope. Although I can get that all shut down now. I have not really been paying attention to the chat here. Oh, he's asking, well, do you know the Zinc RF sock? Let's see, I've heard of it, but I don't have one and I have not used one. So, yeah. Yeah, those things are incredibly expensive. Well, I guess. Yeah, I do have a handful of different FPGA development boards, but a lot of those have actually been donated, so, I'm not going to drop 10 grand on a dev board. Although, I guess flip side is that I don't really work on too many of those applications myself, so I wouldn't really have much use of an RF SoC personally at the moment. Maybe that could change going forward. But up until now, I've been mainly doing, datacom type stuff, which, while tricky, is not, analog RF type tricky. Wait, but how much was this one? Let's just say these boards were an eBay special. Yeah, this. I think I paid like $1,200 for this one. So yeah, it's expensive, but definitely not the same order of magnitude. And then we have a couple of these, in the lab and whatnot. So let's see. All right. Well, let's see. Do we have any more questions in the chat here, or is it time to wrap this up? So we got the high tech. Yep. I saw it on eBay. I'm like, I'm just gonna buy that. Because they never show up on eBay. That's like those are like the only ones I've ever seen. So I saw it. I'm like, okay then. I think we can do some fun stuff with that. Now, actually, we've previously bought some high-tech global boards for some experiments in the lab at UCSD. We bought a pair of their gigantic Vertex 6 boards, and so those things So that was a Vertex 6 HXT 565, and they have 24 10G serializers, which, I mean, comparing it to this, UltraScale Plus device that has 72 25G serializers, I mean, that's nothing. But at that point, that was like the equivalent of one of these guys, right? State of the art. So those were very expensive boards, and we got these QSFP adapter cages for them. Actually, let me see if I can pull up. Let me see if I can pull up that on here. Let's see, I think I have, okay, well, here's the high-tech global board that I have now, these guys, but I think, let me see, they might still have the Vertex 6 one listed on here somewhere, maybe. No, it wasn't that one, it was, this one, yes. So we ended up getting 2 or 3 of these guys. And with those, you can get these adapter cages here where you can plug in. Assuming this wants to load. What the heck? Come on. Oh man. All right, never mind. I guess there's a picture of it right here. So with this, you get 12 SFP Plus modules that are connected through these AirMax connectors to the Vertex 6 board. So this also has a set of retimer chips on here. And actually, this is one of the things that you have to deal with when you're working with these high-speed signals. Is sometimes it makes sense just to regenerate the signal. The idea is that you can receive the signal and basically clean up all of the jitter. You detect all the bits, and then you transmit it on again. So that's what these chips on this board do. They're PHY chips where you have 10G serial on both sides. So you get there's 6 chips on here. Each one's 2 channels that handles all 12 of the SFP pluses here. So the other annoying thing about some of High-Tech Global's boards is just the way they wire stuff up. So on these boards, all of the TX disable pins on all of these modules were connected to GPIO pins on the PHY chips. So the first time we tried to plug optical modules into this thing, it didn't work. And we're like, what the heck is going on here? Why are we not getting any light out of this thing? Well, the TX disable pins need to be flip-flopped. So the first thing we ended up doing is actually soldering some wires on the back of the board to tie the TX disable pins the right way, because I didn't want to sit down. We didn't have any documentation for the PHY chips, so I had to sit down and solder these wires on here to get those things to turn on. Yeah, and I actually made a similar change to these the High-Tech Global boards that I just bought. Like I mentioned before, all of the voltages on here were set wrong, so I had to go in and fix that. Right, there were 4 resistors I had to swap for that, but then they also put these footprints down. Let me zoom in over here for the LP mode pins on the optical modules. So let's see, where are we? Here we go. Yeah, so this is R471, R473. These are little resistor footprints they put in. So I went and shorted all those to ground so the optical transceivers actually turn on. I guess you can actually go poke at those over I2C and turn them on that way. But if you have this board turned on, you're going to be using the transceivers, so you might as well just, force them on. And that's kind of been a recurring theme of pulling the LP mode pins the wrong way or forgetting to pull the LP mode pins. I've had to, rerun designs through Vivado, multiple times due to setting these low-speed GPIO pins the wrong way. Anyway, it happens. And then you add that to your mental checklist. So the next time you build the board, you take a much more careful look at the schematic and make sure you pull the pin the right way. Any suggestions for porting it to the 8v3? Let's see, the 8v3 board, that was, I forget what FPGA is on that. I mean, if you want to port it, it shouldn't be that big of a deal. Probably start with, find a board with a similar FPGA on it and make a copy of that and then adjust the pin assignments. And that's generally all that you need to do. But yeah, other than that, I don't know. again, in terms of, oh, so that's for Verilog Ethernet. Yeah, so that shouldn't be that big of a deal at all. It's mainly about getting the transceiver settings correct and getting it hooked up to the right pin. Finally hearing from someone who has the same issues. What? Tying pins wrong and then having to wait an hour for Vivado to resynthesize the design? Yeah, I guess that's a common problem when working with FPGAs. That's why I commit all my stuff to Git, so the next time I'm working on the same board, I can just pull up a known good design and work on that. All right, well, any more questions, or should we wrap this up? Would you be open to connecting? Yeah, sure. I mean, why not? Yeah, you can look me up. I think you can just put in my last name and that will, and you can narrow it down from there pretty quick. Yeah, an educator of some sort. Well, I am, I'm currently a postdoctoral researcher at UC San Diego. So I'm in academia, kind of more on the research side. We'll see. I may get roped into teaching a class at some point, but we'll see about that. Could be interesting. The main thing for something like that is just to have more people that are, you know, at UCSD that are, you know, competent at working with FPGAs. Yeah. Okay. Oh, no problem. It's been fun. All right. Well, if there's no more questions, then I think I might sign off for now. Oh, do you use Discord? Discord. Oh, I'm not on Discord. Google Group. Oh, in terms of which Google Group? I have one for the Corundum NIC. Other than that, I don't think I don't have many things on Google Groups at the moment. Mainly, I do a lot of stuff via email. Let to know what you think of my low latency 10G Ethernet core. Well, is it open source? I could take a look at it, I suppose. All right, well. All right, I guess if there's no more questions, then I will go ahead and sign off. See you guys later.